Ready? So what are we trying to find? An infinite limit or a limit at infinity, or could it be both? Okay.
Both.
Both, because we're trying to find a limit at infinity, but the answer might end up being infinity, right? We don't know, but I don't think it's going to be infinity. It is going to be a nice little number. What is that number? If I change that to a positive 4x4, 4x raised to 4, not negative. Can you tell me what that number is? Let's go and look at all the cases that we wrote. Not obvious to say, but we like to write close. Almost there. Who gave me 1/2? Alison?
I say it's 1.
You say it's 1.
I thought you wanted to
1/2 is closer than 1. And it's problem, but it is not 1/2. It's a 1/2.
It's 0. Oh.
0.
Yeah.
We don't want to know your final exam score. Okay, 1/2 is inside the root. Oh, it's 1 over square root of 2. But you guys are on the right track. So I know the answer already because I gave you some pointers, some tests. So numerator power is equal to the denominator power. So the answer must simply be the coefficient of the numerator divided by the coefficient of the denominator. By coefficient, I mean the leading coefficient, the one with the highest degree. What's your name?
Jason.
Jason. Jason gave me an answer of 1. I can sort of see why he divided that by that. Right? It has to be the leading coefficient, the coefficient of a term with the highest degree, and in this case, it's x raised 4. So inside the square root, we'll have 1 over 2, which will give us 1 over square root of 2. Good. This is great, but I do have an obligation to explain as to why this is true, especially if you go to advanced math. I'm going to start here. You don't have to do this in the homework, but this simple approach is needed with other functions, tangent, exponential, radical functions, logarithmic functions. The approach is quite simple. I'm going to pull x raised 4 outside of the numerator. X raised 4 comes out, yes. So what should go here? If x raised 4 comes out, can I do that? Yes. If I distribute x raised 4, I'm going to get x cubed. Denominator going to do the exact same thing. Going to pull x raised 4 out. Should have wrote it in decreasing powers of x, but oh well. what would happen to those x-rays for? Will get cancelled. X cubed divided by x raised 4, what will we get?
One over X.
1 over x. Good. X squared divided by x raised 4 is 1 over x squared. X cubed divided by x raised 4, 1 over x, plus 1 over x raised 4. With me so far? Now, what does x approaching infinity mean? If you have to explain this to someone who's got no idea about calculus, and you say x approaches infinity, what are you trying to explain?
Graph is closer to the value that the horizontal asymptote is going towards infinity.
Well, it's the same thing, right? What does going to an infinity mean?
It goes on and on.
On and on, well, if you, what's happening to the numbers as it goes on and on? It's getting bigger, closer.
I was gonna say closer to the horizontal asymptote.
So it's going to get bigger and bigger and bigger. So if I took, that term divided by 10, you have to calculate it. Right, let's try this out. This way will make sense. So approaching infinity simply means we are making x bigger, bigger, and bigger. Other terms. Let's pick 1 over x, and let's start with 10. 1 over 10. What is it? That's an easy question. 0.1. Give me a number bigger than 10. We need to get bigger and bigger, so. You said 10. It's true logically. How about 2000? Let's do 1 over 2000. Get 0.0005. Now 1 over 48,000.
2.08 to the negative 5.
2.08 to the negative fifth power. So as x is getting bigger and bigger and bigger, this particular term is getting smaller and smaller and smaller. Well, if that is true for just any x, imagine doing x squared, x cubed, x raised 4. This is going to explode really fast compared to just x. So when I apply the limit, this term will go to 0. In limits, not exactly. That term is going to go to 0. In limit, that will go to 0. That will go to 0. That will go to 0. Everything is going to 0. Except the 2 and the 4. And that is the exact thing that we had earlier. Do you see the rationale behind it? Again, rational functions, when you do the homework, you can use any of the 4 cases that we discussed and get to the answer. But this particular strategy is essential when you do problems that are not rational functions. Well, to be specific, you have a rational function, but it involves trigonometric functions and inverse trigonometric functions and so forth. Good? Okay. So, even before we start, I know the answer. Do you know the answer? No? Huh? Maybe. What is it, David?
I put 0, but
Okay, do we agree with him? Yes, it is 0. And as a line, what is the equation of that line? Y equals 0, what's its name? Huh? X-axis. How did we come to that conclusion? Well, means I looked at the power there, or the degree there, numerator degree is bigger than the denominator degree. So this is going to approach to 0. Yes,
So 3x² would be bigger than x.
yes,
Because of the quantity.
because it's powers, right? So if you put positive numbers, x cubed is always bigger than x squared.
You forgot to unlock the fact.
So did I say that the numerator degree is bigger than the denominator? Take that back. Denominator degree is bigger than the numerator degree. So we can do the detailed approach just one more time to get comfortable, but we know the answer is x-axis or y equals 0. We pull out the leading term, just the x term. If x squared comes out, I'll have 3 plus x over x squared plus 1 over x squared divided by, well, what should I pull out from the denominator? If I want to go with the same process like the previous problem, I can pull out x cubed, sure. Good. So there is x squared there, there is x cubed there. What would happen? The x squared and the x cubed will get cancelled, leaving you with x. The rest I'm going to write it as is 3 plus x over x over x squared is 1 over x plus 1 over x squared. Here it's 1 plus 4 over x cubed. Good. As x approaches infinity, what would happen to that term? 0. That term. 0. That term. 0. And that's going to leave us with 3 divided by x times 1, correct? That's gone, that's gone, that's gone. So x times 1 is simply x. So now you've got 3, and you keep on dividing it by a huge number. What do you expect to happen to the term inside the root? It would become 0. Square root of 0 is 0. The answer is 0. Good. So, by the looks of it, this might seem different, yes, but there is a radical. Anytime you have a radical, try to convert it to an exponent, and perhaps it should make better sense. So, limit x approaches infinity. Square root of x, I can rewrite it as x raised 1 over 2. Yes? Minus x plus 1 divided by 3x raised 3 over 2 minus x plus 2. Exponent spaces are identical. What do you do to the powers? Add them. So 1 plus half is 3 half. And if we took that detailed approach, that term would go to 0, that term would go to 0, that term would go to 0, that would go to 0. But these two will simply just get cancelled. Do we agree? So the answer would be 1/3. So that's going to go to 0, that is 0, 0, 0, leaving us with just 1/3, so the limit is 1/3. Correct. In that case, we could take the detailed approach just to demonstrate why that's going to go to infinity. I showed you a case where it will approach a number, a case where it becomes 0. I'm going to show you why it becomes infinity. So what would you pull out to cancel from the numerator? X squared, because all I see is x squared in the denominator. So if I pull x squared out, I'll have x cubed over x squared plus 8 over x squared. Pull x squared out, I have 1 plus 4 over x squared. Good. What would happen to the x squared? They will go away. X cubed over x squared will leave us with x. Plus 8 over x squared. There I would have 4 over x squared. As x gets bigger and bigger and bigger, what happens to that term? It'll get smaller, so that would have been 0. What would happen to that term? It'll get smaller and approach 0. The denominator would simply become 1. But x is getting bigger and bigger and bigger. So that becomes 0, that becomes 0. And let's say if x becomes 128 billion, right? Those two would become 0. But that would be 128 billion divided by 1. Yes. So as x gets larger and larger, we'll just end up getting infinity. So this is a case where a limit at infinity is an infinite limit. Does that make sense? Yes. My first step here would be to pull that 16 out x squared out of the root, correct? When 16 comes out of the root, it becomes 4. Yes? Come again?
Does it become positive or negative because you're pulling it out of the root? Or does it
We keep positive. So 4, and when we bring x squared out of the root, we'll simply have x. So that will become 1. And I'll end up having x over 16 x squared. Yes, and minus 4x. Good. When I take the limit, well, before that, let me simplify. The x's would go away, and minus 4x. X approaches infinity, that will go away, correct? So we'll simply have square roots of 1 plus 0. And that would be 4x. That would be 4x. So you may say 4x minus 4x. The answer is. Do you see what I'm trying to say? Well, let's say I apply x approaches infinity. So hypothetically, I can put that at infinity, but that is going to approach infinity. Yes. In here, I'll have 1 plus 1 over 16x. And that is going to approach what number? 0. What about negative 4x? It will approach negative and then infinity. Okay. So in limit, this is the conclusion we are arriving at. Infinity times 1 minus infinity, right? So eventually it seems like we land in this answer, or arrive at this answer, infinity minus infinity. What is infinity minus infinity? 0, right? That's what one would think, but it's not. So then we get something like this. Yes, nice little picture. So what is the answer? I'm looking at that part. Infinity, the y value. Y value is 0. But I already mentioned it's not 0, right? So where did they go wrong? Well, this is why calculus is important. Sure, calculators can't give you the answer, a computer program can, but if you have knowledge about calculus, then we can see things that your naked eye cannot see. Now, what do I mean by that? Well, we're approaching infinity. Looks like things are taken down to 0, but I'm just going to adjust the limit. Let's say I go from 0 all the way up to 20 in steps of 1. Let me start at 0 and go all the way up to 2. What looked like 0 is no longer 0. Yes. Now, what is that number? Adjust the window a bit more, or less than. Now you're starting to see a curve, not the best one, but it is a curve. Reduce it a bit more. Looks like it's flatlining. X window, I'm going to adjust it up to 5 because I know things are just becoming flat. So that is the curve I am getting, and that is the horizontal asymptote. Now, how did we go from negative minus negative, negative infinity minus negative infinity to that? I'll give you a hint. Think of a trick that I mentioned a long, long time ago, not last week, the week before, when we did it properly. There is a radical, n minus 4x, but do you understand the problem at hand? Infinity minus infinity, we would think it is zero, but it's not zero. Now, we're not saying big number minus big number is not equal to zero. What we're saying is in terms of limits, it's not zero. So from here, somehow I ended up with a finite value in the calculator. So the calculator is correct. So what should we do to get to that answer? We have seen this before. You have a cone and you have a jug. Two things, huh?
Use the laws,
Log.
the laws of limits.
Laws of limits, which law? Where did you get laws of limits from cone and jug?
Two different things.
Two different things, right? It's not clicking. Two keywords, cone.
Conjugate.
Thank you, conjugate. So if you multiply and divide by the conjugate, you will end up getting a finite answer. Let's not do that today, we will save that for Wednesday. So I'll show you on Wednesday how we would go from here to that finite number.